In the previous two videos we looked at the energy that's received by the top of Earth's atmosphere, and then what happens as it travels through the atmosphere and is reflected off the Earth's surface. This next step is then looking at what happens with that reflected energy, and some of it is actually then trapped in the Earth system. The idea that we're looking at here is known as the greenhouse effect. And the reason it's referred to as a greenhouse effect, a greenhouse is basically just a big glass house where you grow plants and flowers and those sorts of things. And once energy is absorbed through the glass and transferred to plants inside, that energy can then be trapped, can't necessarily escape back out, and so warming that occurs in a greenhouse. And there are some naturally occurring gases in the atmosphere that are responsible for this greenhouse effect. And we'll have a look at some of them. Some of them you'll probably know about already. They're sort of plastered all over the news quite often, talking about how we're making the greenhouse effect worse, and some of those gases, or the main ones, being carbon dioxide, and I'll just write what the formula are for them here as well. Another one is water vapor. So H2O in its gaseous state. Third one is methane, CH4, and the last one is nitrous oxide, which also can be referred to as dinitrogen monoxide. So it has the chemical formula of N2O. Now, if we consider all of those greenhouse gases, only 1% of the atmosphere is made up of those greenhouse gases. As a side note here, nitrogen gas makes up around 70%, and oxygen gas makes up about 20%. So there are other gases that are in the atmosphere as well. The important thing about nitrogen and oxygen gas is that they don't actually absorb solar energy. So only the greenhouse gases are the ones responsible for absorbing solar energy. Now, there's a couple of things here to note. The greenhouse effect in and of itself is not actually a bad thing. So by having energy being trapped in the Earth system, it means that temperature on the surface of the Earth is at a level that allows life to develop. So important to distinguish between the natural greenhouse effect and the enhanced greenhouse effect. Now, the natural greenhouse effect is something that we can't really do much about. We actually don't want to do much about it. However, the enhanced greenhouse effect is fairly significant, and it's largely due to increased concentrations of greenhouse gases. And the reason why we have those increased concentrations is due to human activity. So the greenhouse effect, as I said, is not necessarily a problem. It's when we have an increase in those gases due to human activity in most cases. However, there are some other factors that we can't control, so things like volcanoes, lots of greenhouse gases spewed into the atmosphere, from some natural processes. However, there's certainly a lot that that mankind has done over the years that could have contributed to that enhanced greenhouse effect. The other thing to note there too, just as I'm finishing this, is that the enhanced greenhouse effect, because there are more greenhouse gases, can trap more energy, and therefore Earth's average temperature can increase. Now, with greenhouse gases, so those four that I mentioned earlier, they absorb ultraviolet and infrared radiation. So when we're talking ultraviolet and infrared radiation, we should identify here that the UV photons, so photons of ultraviolet light, they have enough energy that they can break bonds of the molecules of the gas particles that we find in the air. And the lower energy infrared, while they don't tend to break bonds because they are such low energy, what they can do for specific wavelengths is cause a resonance in molecules. So when we're talking resonance, we're talking about that idea of a natural frequency that the molecules will oscillate at, and as I say, it's only for specific wavelengths. But as a result, both of those have an effect on molecules of gas that are in the atmosphere. Now, when we talk about visible light, it isn't readily absorbed by greenhouse gases. And so it's actually absorbed on the surface of Earth. Once the Earth has then absorbed that, that energy then can be re-radiated by the Earth's surface. So it's not just that it's absorbed and that's the end of the story. That energy can be re-radiated, mostly in the infrared spectrum. So hopefully you can see here that we have, while the visible light isn't initially absorbed by greenhouse gases, given that it's re-radiated mostly in the infrared range, that can then be absorbed by the greenhouse gases. Once the energy has been then absorbed by the greenhouse gases, it can then be re-radiated again. But in this case, it's not just going to be, well, from the surface of the Earth, it has to be upwards. But for greenhouse gases, the energy can be re-radiated in all directions. And so some of that will actually be then directed back towards the ground again. So we have this idea then of the energy being trapped because it continues to be radiated by the ground and then back to the ground by the greenhouse gases. When we consider all of the factors of the energy that's absorbed by the Earth's atmosphere, how it's then transferred to the surface of the Earth, reflected by the surface of the Earth, or re-radiated, and then again trapped by the greenhouse gases, we can identify that that system is in a dynamic equilibrium. So what we mean by that is that the total solar radiation received by the system is equal to the energy that's radiated away from the Earth. So all of that energy that's received from the sun doesn't mean that and that nothing else happens. We do have the Earth that can then reflect some of it, some of the radiation from the re-radiated energy from greenhouse gases can then travel out into space, and so we get this dynamic equilibrium. And what we mean by that too, the dynamic aspect, is that it's not that it's reached a set equilibrium and it stays there. Earth's temperature has actually had to change over billions of years in order for it to be maintained. So it had to increase over billions of years due to all of the changes that have occurred throughout Earth's history. And that's largely due to the fact that Earth's albedo has changed over that time. And the reason why the Earth's albedo has changed is due to things like increased amounts of vegetation over the surface of the Earth, different ice ages that have occurred, continental drift, other geological processes like volcanoes and those sorts of aspects that have had a significant impact on the amount of energy that the Earth has been able to absorb and reflect. Now, if we then look at that balance, so the energy balance of the Earth itself is really quite complex. But rather than get into the complexity, we're going to have a look at a diagram that summarizes it fairly well, and gives us a bit of an insight as to where energy is coming into the system, how it's sort of bouncing around through the system, how it's being re-radiated, and where it's being absorbed. And this diagram is something that you should make yourself familiar with, and so that you can sort of fairly quickly and easily identify various aspects of it, how the energy, as I said, is being reflected, radiated, and absorbed. So to have a quick look at this diagram, the first thing to note is the incoming solar radiation. You see that value there of 341 watts per square metre. That's a value that we talked about a couple of videos ago. And basically, if you just sort of follow the arrows through, you can see that there's some here that's reflected by the atmosphere itself, being 79 watts per square metre. That combines with energy that's been reflected by the surface. So energy that's the reflected solar radiation is then 102 watts per square metre. You can see down here there's 161 watts per square metre that are absorbed by the surface. Some of that's then re-radiated through surface radiation over to the side here. We also have some evapotranspiration and thermals, so some energy being re-radiated from the Earth in that way. We also have some of the incoming solar radiation being absorbed by the atmosphere, so 78 watts per square metre. We then have all of this radiation, or some of it, emitted by the atmosphere and the surface radiation then escaping being 239 watts per square metre. You'll notice that we then have some energy being re-radiated back to the surface. So we get this. So this kind of aspect over here is the greenhouse effect in particular, so obviously the greenhouse gases there being critical factors. So some key things there that you need to be aware of about the energy flows that occur around the Earth, where the energy is reflected, where it's absorbed, and where it's re-radiated.